In 2011, the Internet officially ran out of standard addresses. Yet billions of new phones, smart TVs, and laptops have connected online without a hitch. This chart shows standard IPv4 Internet addresses. The flat line represents the maximum capacity, 4.3 billion addresses. The rising line of global devices completely overtook that limit years ago. Every piece of data needs a destination. Without a unique address, a device cannot receive data. Service providers realized they could stretch their limited supply by changing how they hand out addresses. Instead of assigning a unique address to every single phone and computer in your house, they give your entire home just one shared address. This creates two distinct zones. Inside, a Wi-Fi router assigns a private address to each device, but out on the global internet, everything relies on public addresses. This diagram shows what happens if a private device tries to reach the public internet without any translation. The public internet router sees an address it isn't allowed to route, and it rejects the request. The connection fails. To keep the internet functioning, engineers built an invisible bridge between the private and public zones. They called it Network Address Translation, or NAT. Imagine you sit down at your laptop, which has a private address of 10.1.1.1, and you click a link to a website. Your laptop sends out a request for that web page. This diagram shows the router's first job. The NAT router strips away the laptop's private 10.1.1.1 address and replaces it with the household's public 210.1.1. The request continues to the destination server. To that server, it looks like your router asked for the web page, but the router needs to remember who asked. This table shows its ledger tracking the swap between your device's private address and the router's public address. When the web page data returns, the router checks its ledger, performs a reverse translation, and passes it inward. Because this two-way masking process happens automatically, an entire network of home devices can invisibly piggyback on a single public connection. This still leaves one logical hurdle. If every device in a house shares the exact same public address, how does the router distinguish between two devices if two phones request different websites at the exact same millisecond? This table shows port address translation, handling simultaneous traffic by adding unique port numbers, like :1025, to the shared public IP. Think of the public IP as an apartment building's street address, and port numbers as individual unit numbers, keeping thousands of deliveries organized. This specific technique, often called NAT overload, is what powers almost all modern homes and small businesses, maximizing our limited supply of internet addresses. Hiding all those private devices behind a router has an unintended but highly valuable side effect. It creates a basic layer of security. Because internal devices do not have publicly reachable addresses, unsolicited malicious traffic from the internet hits a dead end. If there is no corresponding record in the router's NAT table saying a device asked for that data, the router simply deletes the incoming packets. However, this strict gateway causes headaches for applications that rely on direct two-way communication, like voice calls or online gaming. The router blocks those incoming connections, breaking the direct peer-to-peer link. To get through these barriers, developers use relay servers just to help devices find each other and negotiate a connection. Ultimately, a permanent fix is rolling out. A new addressing standard, known as IPv6, provides an effectively unlimited supply of addresses. It ensures every device on the planet can have its own unique public identity, removing the need for address translation entirely. While the shift to IPv6 is the long-term goal, the transition is slow. Until then, network address translation remains the mechanism that keeps the modern internet running smoothly every single day.